All right, we're going to solve trigonometric substitution integrals. These are different than just trigonometric integrals because here you're going to need a triangle to solve these integrals. And notice that only part of the integral that you need to look at is what is under the square root. That's because sometimes we're going to actually solve this integral. Oops, let me take that off first. We're going to solve this integral here. And you see that there are other parts. There's this part and obviously dx, but what you need to determine what type of triangle you're working with, and that is the first step with trigonometric substitution integrals, is just this part. One of the sides of the triangle that you're going to use to solve these types of integrals is going to be this expression itself. Now, which side of the triangle equals to this expression? That is up to you to determine. And yes, there is right answer and wrong answer, and there's only one side that needs to be this. And hypotenuse is guaranteed given to you. Let's talk about that a little bit. I like to spend a lot of time labeling sides of the triangle because triangle in trigonometric substitution integrals is the most important part of the solution. So hypotenuse is side that you're subtracting from according to Pythagorean theorem, right? That you subtract from the hypotenuse squared to find the third side. Never from one of the sides. You never subtract from one of the sides because that's not the formula. So, and also this needs to be larger side. Otherwise you would get negative in the square root, and that's a problem because negatives can't be in the square root, but also because negative numbers can't represent length. So in these two cases, since there's a minus sign, what comes before has got to be the hypotenuse based on Pythagorean theorem. Now in this case, this whole expression is the hypotenuse because no other side of the triangle except from the hypotenuse equals to squares of the other two sides, right? So this has to be the hypotenuse. So this is how you determine the side. So hypotenuse, you already know. Then the vertical side always likes to be variable, not the number a, but variable x, okay? Usually, you can see. And even here, it starts with x because it's like, right, it's a function of theta, and theta is star of the show. Okay, so we're going to solve this problem here, and you're going to really understand why triangle is so very important. As you can see, I have a lot of things going on here set up, right? Because you're going to need to keep your notes organized. There's a lot of little elements in the solution, so I kind of came up with this like setup, but you can come up with your own. So here, this is the part of the integral we're going to look at to determine sides of this triangle. You see how this is only illuminated and this part I'm not looking at for now. Okay, based on our analysis, this has to be the hypotenuse. Now, I personally like to label my sides of this triangle without the squares, but you can have it like 9, right? Because what was given to me was 9, but I like to write it in this form, a squared form. But what you shouldn't do is label some sides that are squared, for example, 9 here, and then x here instead of x squared. Either all sides should be squared or none of them should be, okay? So that you don't make a mistake. Then the vertical side wants to be the variable. It varies because of theta. And then the base of the triangle ended up being that expression itself. Okay, and that's under the square root because I like to have all the sides, as I said, without squares. If I wanted them squared, this would be without the square root. Now I have all 3 sides of the triangle labeled. Next step is to write down different ratios, and I can write down maximum of 6 different ratios when we are dealing with 3 different sides of the triangle, right? If you have 3 options, there are 6 different ways to divide them. And trigonometric functions are nothing but different ratios of the sides. Now I'm going to choose the ratio that suits me. And how do I know what I need? Here is where the list of stuff I need comes in. Do you see how I actually wrote out everything that I need to express in terms of theta? So here I need to get dx written in terms of theta and d theta, right? I need to get rid of x's. Everywhere I see x expression, I need to get rid of that because I need theta expressions. And this is what's giving me information based on what I need. I'm going to choose ratio that gives me expression for this. So if I wanted to express this side, I naturally would pick ratio that includes this side, but there are 4 of them. Which one should I go with? And this is very important. Since you're trying to express this right here, and you're moving away from x variable and trying to move into theta and trigonometry, you never want to connect it to another x because you still have to get rid of that. So you wouldn't want to connect this expression to x expression, right? Ideally, you would connect it to a number because that way things would be simple and nice. And of course, you would want the adjacent side to be at the top rather than at the bottom because then you would have to like bring it up, right? So all of that gets checked off by cosine function, and that's exactly what I'm going to use. You see, that's the thinking. And this is kind of the translation because what we're ultimately doing with trigonometric substitution integrals is we're translating, quote unquote, translating dx interval in terms of thetas and trigonometric functions and solving d theta integral, trigonometric integral, because it's going to be so much simpler to solve that integral, practically speaking. So it's a very practical thing while we're doing this. Along the way, though, we are choosing the triangle that is actually sitting there. According to the Pythagorean theorem that I spotted here, there's this exact triangle. If I labeled the triangle incorrectly, then I'm saying that some other triangle than the one that is actually there, or I can actually assign to, is sitting there. So that would be a mistake. That's why labeling sides is very important. So here I'm going to say that this is the adjacent side. Okay, this is the expression. Of course, I'm going to explicitly express exactly what I'm after. So this equals to 3 cosine theta. So I already got expression for that. And here, that expression will be rewritten as 3 cos theta. Do you see how I'm working on writing a new interval? And I'm never going to solve this interval. I'm going to solve this interval and translate back my final answer in terms of x in this step. But first I need x. Now I expressed that, now I need x. I need x for 2 things, because I need x squared and because I need dx. You're always going to need x for trig substitution integrals because you're always going to need to express dx, correct? And dx is nothing but derivative of x. So first you need to express your x. Now going and trying to choose a ratio that also checks off those boxes that we discussed. And I think this is it. It connects the desired side, which is x, to a number. And that's exactly what I would want. So this is the ratio that we're going to use now. And that is again, explicitly express x here as well. Now, derivative of that is simply 3 cosine theta, because derivative and d theta, don't forget that, because derivative of sine theta, and you keep the coefficient, is cosine theta, right? So that's the derivative. And the next square, might as well express that as well. That will be 9 sine square theta. Okay, so I got x squared and dx. So I already have my new integral. Do you see how useful the triangle was? So x squared, I'm going to write an expression for that. That was 9 sine square theta. And dx, instead of dx, I'm going to write 3 cosine theta d theta. Okay, let's copy this integral and solve it. Notice that I'm going to solve d theta integral, which is the purpose of why we did all of this. And this is going to be such an easy integral to solve. These get canceled. Usually a whole lot is going to get canceled with these integrals. 1 over 9 is a constant, so let me bring that out. And I'm left with 1 over sine squared, and 1 over sine is cosecant theta. 1 over sine squared is cosecant square theta. And that is one of your basic rules of integration. If you look in your formula sheet, you'll find it. If you also remember derivative of cotangent, then you would know. So it's negative cotangent theta plus, you're not done yet. The last thing left to do is to, now that you have your answer in terms of theta, go back to your initial variable, which was x. So this is once again where you're going to appreciate how useful this triangle is. So cotangent theta, you know that, is ratio, and that is 1 over tangent, right? So it's adjacent over opposite side, and that's all you need. It's adjacent over opposite, and that's exactly what I have, adjacent to theta over opposite. So you can copy and paste expression for cotangent. If I got any other trig function, I could easily find, can't forget negative 1 over 9, easily find that trigonometric function with the help of my triangle. This is the final answer.